If you haven't got your report, you have to shoot me an email with the email you want me to use and I will get it to you. Just out of curiosity, did anybody get an email with your grade on it? Okay, it arrived. So let's get started. We're going to work on chapter 10 today. A little overlap, parametric equations. Just to show you don't need to use T, you can use any letter of your alphabet. In this case, the X coordinate is 4 cosine theta and the Y coordinate is secant squared theta. But you could have called it 4 cos T and secant squared T. And you can put that guy into Desmos, and I'll show you what it looks like, because it's actually pretty boring, but just to show you what it looks like anyway. That's what it looks like. And so you put like coordinate brackets, the X and the Y. I just decided to use T because I couldn't be bothered trying to find out where the theta symbol was. And it's actually very boring because it has a vertical asymptote at 0. If you keep zooming out, you'll see it. It's basically just a little curve. And parametric curves have a direction, don't they? You can go up or you go down, there's a little arrow on it. So if you're trying to figure out which direction the arrow is, because it doesn't show you in these diagrams, pick a couple of T values, like T equals 0 and T equals, pi upon 6 or something, and that'll tell you where the first dot is and where the second. And you always travel right from T equals 0 to T equals 1 to T equals 2. So Desmos allows you to sketch things, thank goodness. And we're on the first section. So here is our little job. How do you convert this guy, the one that we have here? Excuse me. There, got it. I'm just finding the question here. I got it, right. How do you take this guy and turn it into Cartesian? Cartesian is one of those, things with X's and Y's in. I'm just making that up randomly. We have substitution, right, where you pick one of the equations and make it X equals, right? Any suggestions for this one? Because when trig is involved, all bets are off. You have to just figure a unique way of dealing with the information. So X is 4 cos theta, and Y is going to be secant square theta. And is there anything you can do here that might work?
Would you switch it to the Y equals 1 over cosine squared? Because it's easier to solve for cosine on the top one.
Right, and if you do this one, won't cosine theta be X over 4? And so you get Y equals 1 over X over 4 squared, 1 over X squared over 16, which you can switch to, there you go. That's it. But maybe the next time, you'll do something different, right? Trig is notoriously variable, and there isn't one method for solving trig questions. And the last one I want to do is, again, the changing from parametric into Cartesian. And this is, whatever it is, question 10. E to the negative 40, and Y is E to the 40. And remember, our goal is, don't expect to get Y equals all the time, but get X, Y plus Y squared equals 4, right? As long as there's combinations X's and Y's, you're finished. How do we remove the T this time? X is E to the negative 40 and Y equals E to the positive 40.
Would you rewrite X as 1 divided by E to the 40? And then you could replace that with Y.
That's the correct answer. Would you also agree that that's a slightly nicer version of the correct answer? Are we good? So converting from parametric to Cartesian is really a matter of changing one or other of them. so that you can replace one in terms of the other. So in this case, we can replace the x by this, or replace this by x, I guess is the right way to say it. Right. And that's the end of that question. So we are now moving on to the second and final section of chapter 10. It's not a lot. We're going to do the calculus of parametric curves. Well, I haven't mentioned this yet. Have you noticed that chapter 10 has really got nothing to do with sequences and series? Has that crossed your thought process yet? You're right, it has nothing at all to do with sequences and series. So don't try and make a connection, because there isn't any except some random connection you can make up. Okay. And after we finish chapter 10, we'll start doing 3D, right? Vectors in 3D and so on. And that will have nothing to do with parametric curves either, right? So get used to things not having much to do with the thing that came before, right? A lot of people find this second half of the course much easier than the first half. So I might cheer you up. So here's our world. There's a parametric curve, and we would like to do some calculus on it. And in particular, we would like to find its derivative. And we're going to use that notation. It works well for these situations. And when you find the derivative of a parametric curve, the derivative will also be in terms of t, right? So don't, dy by dx isn't going to be x squared minus 2y, right? It's not going to look like that. It's going to be t cubed minus sine t over cos t, right? It's going to have a look like that. And there is a formula for it, which is why this notation works really well. Look at that guy. You see the y, dy by dt over dx by dt. Does that kind of make sense if you think of this as almost like fractions? They're differentials, but they're almost like fractions. See, if you took this guy and you divided it by this guy, wouldn't you get dy on the top and dx on the bottom? Doesn't that formula kind of look elegant? It's kind of cool. So you differentiate y with respect to t, and you differentiate x with respect to t. Aren't finding derivatives of parametric curves pretty easy? Don't you just find the derivative of y with respect to t on the top and the derivative of x with respect to t on the bottom, and you're done. There might be, there isn't in this case, there might be some style points to do with it. Right? Suppose I wanted to find the equation of the line at at t equals, I want to make sure I get one that works, t equals pi. So I want to find the equation of the tangent line at t equals pi. Now, when you find the equation of the tangent line, you are actually going to get a y equals 2x plus 1 kind of thing, right? So it's kind of mixing and matching. So let's show you what that would look like. If you find the derivative, it's 2t plus sine t over cosine t. If you want to evaluate the derivative at a point, t equals pi, there's a notation where you just put a big line and say t equals pi. And that's going to be 2 pi plus the sine a pi over the cosine a pi. And that's 2 pi plus nothing over -1. And so that's negative 2 pi. So I now know the slope of the tangent line is that guy. Don't I also need to know what the x and y coordinate of P is? Right. How am I going to find the x and y coordinate of a point where the parameter t is equal to pi? How do you think I should do that?
Pi back into the original equations.
Right. Sine of pi gets you nothing. Pi squared, take away that is pi squared, take away -1, so that's pi squared plus 1. Okay, it's maybe not the prettiest equation in the world, but it is going to work. Y minus y1 is m brackets x take away x1. Y take away pi squared plus 1 is equal to -2 pi, the slope, x take away 0. And then add and then take that away from both sides. So we get this guy plus a pi squared minus a 1. Maybe not pretty, but would you agree you can find the equation of any parametric equation as long as you tell me t, right? You tell me t is 0 or pi. Find the derivative, plug in the value of t, that'll get you the slope. Plug the value of t into the x and y to get the coordinates of p, and then use this guy to get your equation. I just thought it somehow came to me. Right, there is a normal Cartesian curve. I would like to make it parametric. It's very, very easy to take any function that's written as y equals a function of x and convert it into parametric. Watch what you do. That makes sense? Can you see why they probably didn't ask you to do it in that direction? It's almost silly. Any questions about finding derivatives of parametric equations? I've only done one, but does it seem it's got its own little formula? Derivative, derivative, try and make it look pretty. Let's see if I can find one. Okay. This is a version of question 1, so it should be nice and easy. The parametric is 4t cubed plus 3t, that's for y. X, I should say, and for y, it's 6t take away 5t squared. And they make a meal of it, but essentially that's what you're after. So you differentiate the y with respect to t and put it on the top. You differentiate the x with respect to t, put it in the bottom. This is really Calc 1 stuff. That guy gets you 6 take away 10t. This guy gets you 12t squared plus 3. Anything you could do, style points? Not much, but you can do something. You want to tell me what you could do? After you do it, it's probably not worth it, but at least we should try it. 6t take away 10t. 6 take away 10t. What could you do?
You could pull out a 2-factor.
Yeah. Would you agree it doesn't do much? And you could pull out a 3 on the bottom. That would be an example of a style point that wasn't really much. Would you agree it doesn't really bring any to the party? But sometimes, can you imagine that that 2 and that 3 might cancel and you get a little bit nicer answer? Let's pick essentially the same question. We have x equals the square root of t. Y is t squared, take away 2t. T is going to be 16. And they want us to find the equation of a tangent line. First thing I would do is find the derivative. Well, that guy is 2t take away 2. I know it's ages. You can't really find the square root of t. Don't you have to call it t to the half if you want to differentiate it? Okay, so now I've written it as t to the half. When you differentiate it, it's 1/2 t to the negative a half. So the top line is this guy. And this is not pretty. I want to do some style points on this. Any suggestions what I could do with this ugly 1/2 t to the negative a half that's in the denominator? This is pure algebra. What could I do with 1/2 t to the negative a half? Because right now it's nobody's friend.
Couldn't you flip the half and also bring up the t to the negative half as a positive 2 and a t, and no, a square root t?
So if I pick up right, this is what I hear. That negative comes upstairs. A half on the bottom, isn't it? 2 on the top. So actually, we don't have a fraction here. And if I picked up correctly, you also want to call that guy the square root of t. Does that make sense? It's nitpicky, but it's there, so we should do it. Is there anything left? Or let's phrase it a different way. What's left? I can do a little bit more. Not much, but I can do a little bit more.
Factor an extra 2, so it's 4 square root of t, t minus 1.
Now, when you were in Calc 1, which probably feels like a lifetime away, some of the things that you were asked to do with the derivative was to find out what are called critical numbers. These are places where the derivative is 0. Because when a derivative is 0, don't you very often end up being at the top of a hill or at the bottom of a valley, right? When you have done nice style points to these, can you see that it's easier now to find out where the thing has a 0 derivative? Would you agree at t equals 1 and at t equals 0? Isn't that the only place where this curve can have a hill or a valley? It may have a horizontal point of inflection, but pretend they don't exist, right? Hills or valleys are more likely anyway, right? And that's what makes that good. Well, in this case, we want to find this equation of the tangent line at t equals 16. So we're going to find the derivative at t equals 16. And it's going to be 4 times the square root of 16 times 16 take away 1. And that's what? 4 times 4 times 15. Oh, God in Himmel. 240. What a big slope. Are you comfortable about this slope being 240? Provided I can count. Does that look reasonable? Big, but that's what the answer is. Well, that's step 1, find the derivative. Step 2, find the coordinates of the point. Well, we've done this before. If t equals 16, won't the x coordinate of p be the square root of 16, which is 4, and that the y coordinate will be 16 squared, take away 2 lots of, oh God, in Himmel again, 256, take away 32, 224. So P has the coordinates 4, 224. And to finish this question then, we can now find the equation of the tangent line. Because we know the slope is 240, and we know that the point it passes through is this guy. So it's going to be y take away 224 equals 240 x take away 4. And I'm getting bored with this question. Can I do ... and you'll get some ridiculously big straight line? I mean, the hard part's over. So finding the equation of a tangent line is really just an extension of finding the derivative and using it. I'm just scanning through here to see where that goes. So that gets you, we've pretty much covered questions 1 to 6.
Can I see step 3 real quick?
Sure. There we go. So what's happening in question 7 is not as pretty. How to find second derivatives of parametric equations.
I'm good now.
Okay. You won't like this one. I think the first derivative formula is really elegant, right? So dy by dx is dy by dt, right? Differentiate it with t, and on the bottom, differentiate the x with t. The second derivative looks like that. That's the notation for second derivatives. I know we don't use it much, but that means second derivative. It has a formula, but it's not a pretty formula. It'd be a miracle if you could guess this, but I'd be really impressed if you did. Anybody want to have a guess at what the formula for the second derivative is? Because it is intuitively not that clean. None of you brave, none of you feel lucky. Okay, don't blame you. You differentiate the first derivative, right? Dy by dx, ugh, my x looks weird. My dy by dx with respect to t. Oh, that kind of makes, remember this is going to be a function of t, isn't it? So you can differentiate the first derivative with respect, right, to t, and then you differentiate dx by dt again, and you stick it in the bottom. That is not intuitive, is it? But that's the formula. Do you want to see a pseudo proof of it? Okay. I want you to think of these not quite like fractions, but similar to fractions, right? So if you take d by dt of dy by dx, and on the bottom, we've got dx by dt. This is like d squared y dt dx, great? And on the bottom, we have dx by dt, which means you can take the top guy And dividing is the same as multiplying by reciprocals. I wish my x's, I'm going to have to write this again. My x's are beginning to look like t's. Right, so this is the same line, but drawn a little bit cleaner. Do you see the dt's cancelling out? Do you see a dx times another dx, which is called dx squared? Do you see the derivative formula? We good? Right. Actually, that went smoother than I thought, because a lot of people find that hard to get their head around. So let's pick a question and find the second derivative. So I think it was question 7. So let me scroll to 7. X is t squared plus 9. Y is t squared plus 3t. Thankfully, they're doing it with polynomials. If you made these really ugly, this becomes horrendously messy algebraically. So we have to find dy by dx first. And that's differentiate y with respect to t on the top and differentiate x with respect to t on the bottom. And this guy gets me 2t plus 3. And this guy gets me, what's that, 2t? So far, so good. Now, I could certainly leave that alone and then just plug this formula in, and that would be nothing wrong with that. If I decided to do this, wouldn't my next line be differentiate this fraction with respect to t all over, just differentiate x with respect to t again, right? And nothing wrong with that. Can anybody see where that came from? How did that become this guy?
You distributed 2t on the bottom?
Yeah, so I divided. So I essentially said this guy and this guy. Any suggestions for why I've decided to go this way instead of just doing the quotient rule, which would work? Why do you think I decided algebraically to go this direction?
Because it's just a lot less terms and the one's going to disappear and then it's less fractions to mess up.
Pretty much it. You should know your weaknesses. I am careless. There's a shock to you. So if I can avoid quotient rules inside divisions, inside other things happening, you know, I'm less likely to make a mistake, right? So that is not something you need to know. It's just this particular question lends itself to that. So second derivative is differentiate the first derivative with respect to t and divide by another dx by dt. Well, if you differentiate this with respect to t, you get negative 3 over 2 t minus 2. And if you differentiate x, you get 2t. And that becomes negative 3 over 2 t to the negative 3. And because of the negative powers, I'd probably rewrite it like that. I'll be comfortable with the final answer. Negative 2 divided by that gets you negative 3. 3 halves. Oh, why did that? Nobody knows my mistake. I even managed to still make a mistake even though I chose a route.
Would it be 4 on the bottom instead of 2?
Well, it's 4 on the bottom because what?
Because the 2's didn't cancel. It was divided by 2 and then a 1 over 2.
Right, so I did that to try and avoid mistakes. I still managed to make a mistake, but at least it was one that I could catch pretty quickly. Okay, let's do another one of these second derivatives. I might as well do this one. E to the t, e to the negative t. Got to find the first derivative. There's our standard formula. To divide or to find the derivative of this with respect to t, it's a little baby product rule. So it's 1 times e to the negative t, pardon me, minus t e to the negative t. That's what you eventually get. And this guy gets you an e to the t. And so what we got here, I've got this guy over this guy, so that's e to the negative 2t, and this guy over this guy is minus t e to the negative 2t. And I can pull out this guy to here. Okay. Actually, I could get that answer a slightly better way. If I pull out e to the negative t as a common factor, couldn't this one come upstairs and that would get me the same result? That might be a little bit cleaner. Are you comfortable with what the thing is? Now, couldn't I also call this 1 minus t over e to the 2t? In other words, make it a fraction. Because I'm going to be differentiating in a few moments, do you know why I'm leaving it as a product rule rather than a quotient rule? I'm better at product rules, right? They're less work, that's all. You could do it as a quotient rule. Now, I'm not going to do the whole thing here because it is a long question, but to do the second derivative, you differentiate this guy with respect to t. So you're going to differentiate that guy. And it's going to be over dx by dt, which is just e to the t. So can you imagine doing a product rule and then dividing everything by e to the t? You should be good. So, dot, dot, dot. I'm just doing a quick check, see if there's any more second derivatives. No, okay, good. That was the end of the second derivatives. We're now going to look at finding horizontal tangent lines and finding vertical tangent lines. So we're only going to be finding first derivatives again, because that's all you need to use if you're looking for horizontal or vertical. What is the derivative dy by dx equal to when you're getting a horizontal tangent line? Big fat zero. And what is this going to be equal to when you find a vertical tangent line?
Infinity?
Well, let's do a boring, parametric curve, right? At this point here, won't the tangent line be vertical? Great. And vertical happens when the derivative is infinite. Great. And there's other places of 1 over there, for instance. Now, if you're going to be horizontal, do you see that it could happen here, happen here, it could happen here, happen here? Right, quite a few places. But when you're horizontal, tangent line, isn't the derivative 0? Does that make sense? Zeros give you horizontal tangent lines. Undefined or infinite give you vertical ones. But remember the formula for calculating dy by dt. It was made up of 2 pieces. Right? A dy by dt on the top and a dx by dt on the bottom, right? So, if the derivative is 0, which one of these is the only one that needs to be 0 for that to happen? So say it again. If the derivative is equal to 0, which one of these two, dy by dt or dx by dt, which one is the only one that needs to be 0?
dy by dt.
Right? You only need the top to be 0. So if you are trying to find when is a parametric curve horizontal tangent line, don't you only need to find when is dy by dt equals 0? You don't care what the other one is doing because it doesn't really matter. What about for a vertical tangent line? Anything going on here that you only need to look for to make it vertical? Which one of these two needs to be a certain number for you to get vertical?
dx or dt.
Isn't there a nice kind of symmetry about that? That horizontal tangent lines happen when dy by dt is equal to 0, and vertical tangent lines happen when dy by dx by dt is 0, right? So let's put this into effect. Suppose I'm being asked to find the values of t where the derivative is horizontal tangent lines, right, or where the curve is horizontal tangent lines, or when it has vertical. And I have, this is my x. This is my y. Now, for completeness sake, I'm going to do the whole derivative. Well, this guy gets you e to the t take away 1, and this guy gets you 4t. Take away 4. For some reason, my brain wasn't functioning. Right. If you want a horizontal tangent line, aren't you trying to make this equal 0? But isn't the easy thing to realize is the only thing you really need to worry about is the top being 0. Would you agree the bottom being 0 doesn't help? The bottom can be 42 and it's still going to be 0, right? Well, if you want to solve this, aren't you looking for t equals 0? Agreed? Now, when t equals 0, you will get 0, 0, and 0. Oh, so guess what? At the origin, there's a horizontal tangent line. Now, suppose you're looking for vertical tangent line. Well, we already know the derivative is this, but in this case, aren't you only interested in the bottom being 0? And t equals 1. And what would that point look like? Well, 2 take away 4 is -2, and e take away 1 is just called e take away 1. So at the point with coordinates -2, e minus 1, right, that's t equal 1, aren't you going to have a vertical tangent line? In fact, aren't they the only places where there's going to be a horizontal or vertical tangent line? Right, so this shape can only have one hill or one valley, and it happens at the origin. And it can only have one where it curves back on itself. I mean, when you get vertical tangent lines, don't they happen because the curve, what I'm calling, curves back on itself, right? It does that. So doesn't this shape only have one of each feature? And not only do we know it only has one, don't we also know the coordinates of where they are? So we pretty much know everything that we want to know. Any questions about that? I feel it's going well, but that's what I'm feeling, right? Do you feel comfortable that you can find dy by dx? Right? Maybe less comfortable about the second derivative, ugly formula, but as long as you do it, it'll work. Comfortable about equations of tangent lines at t equals pi or t equals 2? Done that. And now we're looking at, can you find horizontal and vertical tangent lines to parametric curves? We feel good about that. Let's do one more just for fun and giggles. This is question 9. Parametric, there's x, and got that guy. Oh, yeah, let's cut some corners. I want a vertical tangent line and I want the horizontal tangent line. And I'm not even going to find dy by dx. I'm just going to find the appropriate one. Which do you want? Dx by dt to be 0 or dy by dt to be 0 when you're looking for vertical tangent lines?
dx dt.
Right. Obviously the other one, dy by dt. Right. If you differentiate x, you get 3t squared take away 3, which comes out like that. Oh, guess what? There are 2 places where that happens. Are we comfortable about that? 1 and -1. And when's this guy going to be 0? Well, if you differentiate this guy, you just get 2t. That's pretty easy. There's only one of them. Now, you're being asked to find the coordinates of them. Right, so I'll do the horizontal tangent line first. At t equals 0, the x coordinate is nothing and the y coordinate is -8. There are 2 vertical tangent lines, right? One at 1 and one at -1. If you plug in 1, you get 1 take away 3, which is -2, and 1 take away that is -7. And if you plug in -1, you get, good grief, what do you get? You get +2 and -7. There's your answers. So I know that there is only one place where there's a horizontal tangent line to this parametric curve, and that happens at the point 0, -8. And I know that there are 2 places where there's a vertical tangent line, and these are the coordinates of those 2, and only those 2 places where that happens. Okay, I got, let me find this guy. Good. Let's try this one. While I'm doing this, you'll say hi for attendance. And I'm going to do some really dangerous. I'm going to find out if what we said is in fact true. So it's t cubed. Oh, t cubed, right. Take away 3t. I thought I'd got them back to front, but I haven't. Comma, t squared. Take away 8. And I seem to have picked up an extra comma somewhere. T cubed, okay. And t is going to go from, oh, yeah. Oh, you shouldn't need any more of it. I'll do -1 because I want to, and I'll finish it at 2. Right. Now, where are you? There we are. Now I said, it's a little bit hard to see this, but you're going to trust me on this. This guy here, right where my mouse is pointing, can you see that's the end of the curve going upwards? So maybe if I make this -2, we'll see it better. There we go. Can you see the two vertical tangent lines? And can you see the horizontal one? And isn't that horizontal one exactly where I said it'd be, 0, -8? And aren't these two vertical ones at -2, -7 on this side and 2, 7 at the other? Didn't calculus find exactly everything we said it was going to have in the places we said it was going to be? And not only that, if I drew this curve forever, there are no more hills or valleys, right? There's no more places where there's horizontal tangent line, and there are no more places where there's vertical ones. So my best guess is, can you imagine this little loop would just zoom off that way and this one would zoom off that way, and nothing very interesting would happen after that. So we kind of know pretty much everything you need to know about that curve. And we did it all through calculus. Pretty cool.